To us mere humans, our sun feels like an eternal giant, blazing at the center of everything we know. But step back into the depths of the Scutum constellation, and one candidate emerges that shatters every notion of scale. A red supergiant so vast it forces the question, is this the largest star in the universe? Yet how colossal can these fiery beasts truly become? And what hidden limits does the cosmos impose before even they collapse under their own glory? You might think our sun is pretty big, and it is. With a radius stretching 700,000 kilometers, if the sun were a football, Earth would shrink to the size of a tiny peppercorn just 2 millimeters across. Pile together every planet, moon, and asteroid in our solar system, and the sun still outweighs them all by more than 700 times. But among the stars, our sun ranks as utterly ordinary. Nearby twins like those in Alpha Centauri match it closely, while others swell to twice its girth without breaking a sweat. But how big can a star actually grow? To grasp the outer edges of possibility, we turn to the grand map of stellar lives known as the Hertzsprung-Russell diagram. It arrays stars by surface temperature against their total light output, revealing hidden patterns across billions of years. Running like a glowing spine through its heart lie the main sequence stars, where the vast majority spend their longest, steadiest chapters. Here, after the violent birth from collapsing gas clouds, they settle into a delicate truce. Hydrogen fuses steadily in the core, its outward pressure perfectly balancing the crushing inward pull of gravity. This hydrostatic equilibrium keeps them stable, yet no two shine alike. Our sun rests near the middle of this sequence, a modest G-type star with a surface temperature of about 5,778 Kelvin, radiating that familiar yellow-white glow. Inside, the proton-proton chain steadily converts hydrogen to helium, burning through 600 million tons of fuel every single second to power life across billions of years on our world. Shift along the sequence, however, and the pattern sharpens into something profound. Cooler, dimmer stars huddle at the lower right. Hotter, brighter ones blaze at the upper left. Mass dictates the drama. The greater the mass, the fiercer the core pressure, the faster the fusion, the more ferocious the light. Consider a B-type powerhouse like Rigel in Orion's Foot. Its surface burns at over 12,000 Kelvin, nearly twice as hot as the sun, while its mass reaches 21 times greater. That extra weight compresses the core so intensely that fusion races ahead, flooding the star with energy that radiation pressure forces outward in a dramatic swell. The result? A volume more than 6,000 times our sun's. Yet this glory comes with a brutal cost. Massive stars devour their fuel at breakneck speed. Where the sun may shine for 10 billion years, Rigel races through its hydrogen in just a few million, already halfway through its brief, brilliant existence. Such fleeting lives make these giants rare. The universe simply has less time to show them off. So is the largest star simply the most massive? Theory suggests stars cannot stably exceed about 150 solar masses without internal forces tearing them apart. But the cosmos cheats this boundary in spectacular ways. When two heavyweights collide and merge in dense clusters, the newborn giant can surge far beyond the limit, packing 250 solar masses or more into a single, seething core. One such survivor, R13601, sits at the extreme upper left of the Hertzsprung-Russell diagram. A Wolf-Rayet star of almost mythic ferocity. Estimated at 265 solar masses and 40 times wider than the sun, it hurls its outer layers away in relentless winds reaching 3,000 kilometers per second, shedding 10 solar masses every million years. In just 4 seconds, it pours out as much energy as our sun does in an entire year. mostly a searing ultraviolet that our eyes would never see unaided. Its life spans a mere 3 million years, the cosmic equivalent of a mayfly's day. Yet in that flash, it forges the heavy elements that will one day seed new worlds. Still, raw mass does not crown the largest by radius. That honor belongs to stars that have left the main sequence behind. Once core hydrogen runs dry, gravity squeezes the heart tighter, igniting helium fusion and heating the outer layers until hydrogen ignites there too. The star balloons outward in a red giant phase, its atmosphere cooling and expanding as shell burning takes over. Our sun will one day swell to 250 times its current radius, its outer edge swallowing Mercury, Venus, and possibly Earth itself in a fiery embrace. This transformation awaits stars between roughly 0.8 and 8 solar masses, turning modest suns into crimson behemoths that pulse with ancient light. A living example shines in Satis as Mira, a red giant only slightly more massive than the Sun, yet already 332 times wider at baseline, and up to 402 times during its rhythmic expansions every few hundred days. These pulsations send ripples through its tenuous atmosphere, flinging material outward in slow, smoky waves that will one day enrich the interstellar medium. Yet even red giants pale beside their bigger siblings. Cross the 8 solar mass threshold, and red supergiants appear, towering, doomed titans destined for supernova glory. Their cores fuse ever heavier elements in layered shells, each burning hotter and faster than the last, while the outer envelope swells to unimaginable proportions. Betelgeuse stands as one such sentinel, its diameter exceeding 1.2 billion kilometers, more than 700 times the Sun's. Placed at our solar system's center, it would engulf all rocky planets and reach beyond Jupiter's orbit, its ruddy glow turning day into eternal twilight. These supergiants churn with violent convection, their surfaces roiling like boiling oceans, hurling vast plumes of gas and dust that blur the very boundary between star and space. Yet even Betelgeuse does not wear the crown. That distinction may belong to a contender lurking in Scutum, a red supergiant designated RSGC1-F01 within one of the Milky Way's most massive young clusters. Colossal barely begins to describe it. Current estimates place its radius at 1,530 times that of the Sun, a figure that means nearly 3.6 billion suns could vanish inside its volume. Surprisingly cool at just 3,550 Kelvin, it glows with a deep, somber red that betrays its advanced age. At 22,000 light-years away, it remains invisible to the naked eye, demanding infrared eyes and powerful telescopes to pierce the galactic dust that shrouds its home. If centered in our solar system, its photosphere would stretch past Jupiter and nearly kiss Saturn's orbit, a sphere of plasma so vast that light itself would take more than an hour to cross from one side to the other. This monster will not linger. Born in a cluster just 12 million years old, it has already exhausted much of its fuel and now races toward its end. In a few million years more, it may shed its outer layers in dramatic bursts, transforming into a yellow hypergiant whose surface heats dramatically while its radius contracts. These hypergiants pulse with explosive instability, capable of ejecting Jupiter's entire mass in a single violent convulsion. The expelled gas, rich in carbon, oxygen, and nitrogen forged deep inside, drifts outward to form immense shells spanning thousands of astronomical units, clouds that will eventually mingle with other stellar debris, seeding fresh molecular nurseries where new stars and planets will condense from the ashes of giants. Yet even this champion faces rivals whose measurements remain fiercely debated. Far beyond the Milky Way, in the Large Magellanic Cloud, sits WOHG 64, another red supergiant whose latest refined radius reaches 1,540 solar radii with a margin of just 77. Recent observations reveal it dimming noticeably over the past decade, shrouded in fresh dust as it expels material at rates of thousands of Earth masses per year. Hot molecular gas and titanium oxide lines confirm it still clings to its red supergiant identity, though some models suggest it hovers on the brink of yellow hypergiant transition. At 160,000 light-years, precise sizing grows treacherous. Distance errors, pulsations, and thick circumstellar envelopes all conspire to blur the truth. Is WOHG 64 truly larger? Or has RSGC 1-F01 claimed the throne? The question hangs in the data, reminding us how fragile our knowledge remains when stars refuse to sit still. These behemoths scrape against the theoretical ceiling called the Hayashi limit, a sharp boundary on the Hertzsprung-Russell diagram beyond which cool stars cannot stably exist. Push past it, and convection runs wild, gravity regains control, and the star shrinks back toward stability. Metallicity plays a subtle role too. In galaxies poorer in heavy elements, like the Magellanic Clouds, stars can swell slightly larger before the limit bites. Yet even there, the ceiling holds firm around 1,500 to 1,600 solar radii for current cosmic conditions. Newer infrared surveys and space telescopes continue to hunt for outliers, scanning distant clusters for red supergiants that might edge closer to the barrier. Each fresh detection tightens the noose around what we once thought impossible. Yet the universe always seems to find one more surprise. Measurement itself remains an art of exquisite uncertainty. Astronomers rely on the Stefan Boltzmann law. Luminosity equals 4 pi times radius squared times sigma times temperature to the fourth, to back-calculate size from observed brightness and color. But dust obscuration, variable pulsations, and imprecise distances from parallax or cluster fitting can swing estimates by hundreds of solar radii. Gaia's data releases have already slashed some candidates downward, while ALMA's millimeter eyes pierce envelopes to reveal true wind speeds and mass loss rates. Every revision reshapes the leaderboard, turning yesterday's record holder into today's also-ran and keeping the crown in perpetual contest. What drives these stars to such extremes lies in the final fusion stages. After helium burns to carbon and oxygen, the core contracts again, igniting neon, then oxygen, then silicon in a frantic onion skin structure. Each layer burns for shorter and shorter times. Silicon fusion lasts mere days, until iron accumulates at the center. Iron fusion consumes energy rather than releasing it, so when the core turns to iron, support vanishes. In seconds, the star implodes, then rebounds in a supernova that outshines entire galaxies, scattering the heavy elements forged in its heart across light-years of space. Without these dying supergiants, the carbon in our bodies, the oxygen we breathe, the iron in our blood would never exist. They are not just the largest. They are the universe's essential forges. Beyond our galaxy, emerging surveys hint at even more dramatic possibilities. In high redshift clusters, lower metallicity may permit slightly larger envelopes before radiation pressure or pulsational instability intervenes. James Webb Space Telescope. Glimpses of ancient red supergiants already show stars pushing the Hayashi boundary in environments unlike our own. Perhaps in the early universe, before heavy elements polluted the gas, true monsters exceeded 2,000 solar radii. Their light long since stretched into infrared whispers we are only now beginning to catch. Each new detection reframes the question. Is our current champion merely a local record? Or does the cosmos hold titans we have yet to glimpse? The uncertainty only deepens the awe. These stars defy human intuition so completely that our minds slide off their surfaces like water on glass. A circumference that would take a jetliner centuries to circle. A gravity well so gentle at the surface yet so absolute at the core, that light itself struggles to escape the interior chaos. They burn with the fury of creation and the melancholy of impending doom, their short lives the price of their grandeur. And yet, in their death throes, they gift the galaxy the raw materials for everything that follows. New suns, new planets, new chances for life to arise. The universe stretches so far beyond comprehension that even these cosmic monsters shrink to motes when set against galactic arms spanning 100,000 light-years, or the filaments of the cosmic web threading billions. We cannot map it all, cannot visit even the nearest giants, cannot fully predict when the next supernova will bloom in our skies. But that very mystery invites us forward. Bigger is not always better, after all. Our modest sun and fragile blue world have nurtured intelligence, curiosity and wonder across 4 billion years. A quiet miracle nestled inside the roar of giants. If these stellar titans have stirred something profound within you, the shiver of scale, the thrill of discovery, the quiet gratitude for our small place in the vastness, then subscribe to journey deeper into the cosmos together. Drop a comment sharing which colossal star captivates you most, or whether you suspect something even larger hides just beyond our sight. Share this exploration with fellow dreamers who gaze upward at night. And above all, carry the question with you. In an infinite universe still revealing its secrets, what other wonders wait for minds bold enough to ask? The stars are calling. Will you listen?